Magnetism and Matter. Introduction. Magnetic phenomena are universal in nature. Vast, distant galaxies, the tiny invisible atoms, men and beasts all are permeated through and through with a host of magnetic fields from a variety of sources. The Earth's magnetism predates human evolution. The word magnet is derived from the name of an island in Greece called Magnesia, where magnetic ore deposits were found as early as 600 BC. Shepherds on this island complained that their wooden shoes, which had nails, at times stayed stuck to the ground. Their iron-tipped rods were similarly affected. This attractive property of magnets made it difficult for them to move around. The directional property of magnets was also known since ancient times. A thin, long piece of a magnet, when suspended freely, pointed in the north-south direction. The name lodestone or lodestone, given to a naturally occurring ore of iron magnetite, means leading stone. The technological exploitation of this property is generally credited to the Chinese. Chinese text dating 400 BC mentions the use of magnetic needles for navigation on ships. Caravans crossing the Gobi Desert also employed magnetic needles. A Chinese legend narrates the tale of the victory of the Emperor Huangdi about 4,000 years ago, which he owed to his craftsmen, whom nowadays you would call engineers. These engineers built a chariot on which they placed a magnetic figure with arms outstretched. Figure is an artist's description of this chariot. The figure swiveled around so that the finger of the statuette on it always pointed south. With this chariot, Huangdi's troops were able to attack the enemy from the rear in thick fog and to defeat them. Some of the commonly known ideas regarding magnetism are: 1. The Earth behaves as a magnet with the magnetic field pointing approximately from the geographic south to the north. 2. When a bar magnet is freely suspended, it points in the north-south direction. The tip which points to the geographic north is called the North Pole, and the tip which points to the geographic south is called the South Pole of the magnet. 3. There is a repulsive force when north poles or south poles of two magnets are brought close together. Conversely, there is an attractive force between the north pole of one magnet and the south pole of the other. 4. We cannot isolate the north or south pole of a magnet. If a bar magnet is broken into two halves, we get two similar bar magnets with somewhat weaker properties. Unlike electric charges, isolated magnetic north and south poles, known as magnetic monopoles, do not exist. 5. It is possible to make magnets out of iron and its alloys. We begin with a description of a bar magnet and its behavior in an external magnetic field. We describe Gauss's law of magnetism. We then follow it up with an account of the Earth's magnetic field. We next describe how materials can be classified on the basis of their magnetic properties. We describe para, dia, and ferromagnetism. We conclude with a section on electromagnets and permanent magnets. The bar magnet. One of the earliest childhood memories of the famous physicist Albert Einstein was that of a magnet gifted to him by a relative. Einstein was fascinated and played endlessly with it. He wondered how the magnet could affect objects such as nails or pins placed away from it and not in any way connected to it by a spring or string. Examining iron filling sprinkled on a sheet of glass placed over a short bar magnet. The arrangement of iron fillings is shown in figure. The pattern of iron fillings suggests that the magnet has two poles similar to the positive and negative charge of an electric dipole. One pole is designated the north pole and the other the south pole. When suspended freely, these poles point approximately towards the geographic north and south poles, respectively. A similar pattern of iron fillings is observed around a current-carrying solenoid. The magnetic field lines. This is shown both for the bar magnet and the current-carrying solenoid in figure. electric field lines of an electric dipole are also displayed in figure. The magnetic field lines are a visual and intuitive realization of the magnetic field. Their properties are 1. The magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike the electric dipole, where these field lines begin from a positive charge and end on the negative charge or escape to infinity. 2. The tangent to the field line at a given point represent the direction of the net magnetic field B at that point. 3. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field B. In figure, B is larger around region 2 than in region 1. 4. The magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. One can plot the magnetic field lines in a variety of ways. One way is to place a small magnetic compass needle at various positions and note its orientation. This gives us an idea of the magnetic field direction at various points in space. As an equivalent solenoid, Ampere's hypothesis that all magnetic phenomena can be explained in terms of circulating currents. Recall that the magnetic dipole moment M associated with a current loop was defined to be M is equal to NIA, where N is the number of turns in the loop, I the current, and A the area vector. The resemblance of magnetic field lines for a bar magnet and a solenoid suggests that a bar magnet may be thought of as a large number of circulating currents in analogy with a solenoid. Cutting a bar magnet in half is like cutting a solenoid. We get two smaller solenoids with weaker magnetic properties. The field lines remain continuous, emerging from one face of the solenoid and entering into the other face. One can test this analogy by moving a small compass needle in the neighborhood of a bar magnet and a current-carrying finite solenoid and noting that the deflections of the needle are similar in both cases. To make this analogy more firm, we calculate the axial field of a finite solenoid depicted in figure. We shall demonstrate that at large distances, this axial field resembles that of a bar magnet. Let the solenoid of figure consist of n turns per unit length. Let its length be 2L and radius A. We can evaluate the axial field at a point P at a distance r from the center O of the solenoid. To do this, consider a circular element of thickness dx of the solenoid at a distance x from its center. It consists of n dx turns. Let I be the current in the solenoid. From equation 13, the magnitude of the field at point P due to the circular element is dB is equal to mu0 n dx I a square upon 2 r minus x square plus a square raised to 3 by 2. The magnitude of the total field is obtained by summing over all the elements, in other words, by integrating from x is equal to minus L to x is equal to plus L. Thus, B is equal to mu0 n I a square upon 2. Integration from minus L to L dx upon r minus x square plus a square raised to 3 by 2. This integration can be done by trigonometric substitutions. This exercise, however, is not necessary for our purpose. Note that the range of x is from minus L to plus L. Consider the far axial field of the solenoid, that is, R is much greater than A and R is much greater than L. Then the denominator is approximated by r minus x square plus a square raised to 3 by 2 is equal to r square raised to 3 by 2 is approximately equal to r cube, and B is equal to mu0 n I a square upon 2 r cube. Integration from minus L to L dx. B is equal to mu0 n I upon 2 into 2L a square upon r cube. Equation number 1. Note that the magnitude of the magnetic moment of the solenoid is M is equal to N 2L I pi a square. Total number of turns into current into cross-sectional area. Thus, B is equal to mu 0 upon 4 pi into 2m upon r cube. Equation number 2. This is also the far axial magnetic field of a bar magnet, which one may obtain experimentally. Thus, a bar magnet and a solenoid produce similar magnetic fields. The magnetic moment of a bar magnet is thus equal to the magnetic moment of an equivalent solenoid that produces the same magnetic field. Some textbooks assign a magnetic charge, that is also called pole strength, plus qm to the north pole and minus qm to the south pole of a bar magnet of length 2L and a magnetic moment qm 2L. The field strength due to qm at a distance r from it is given by mu 0 qm upon 4 pi r square. The magnetic field due to the bar magnet is then obtained both for the axial and the equatorial case in a manner analogous to that of an electric dipole. The method is simple and appealing. However, magnetic monopoles do not exist, and we have avoided this approach for that reason. The dipole in a uniform magnetic field. The pattern of ion fillings, that is, the magnetic field lines, gives us an approximate idea of the magnetic field B. We may at times be required to determine the magnitude of B accurately. This is done by placing a small compass needle of known magnetic moment M and moment of inertia I and allowing it to oscillate in the magnetic field. This arrangement is shown in figure. The torque on the needle is tau is equal to M into B. In magnitude, tau is equal to mb sin theta. Equation number 3. Here, tau is restoring torque and theta is the angle between M and B. Therefore, in equilibrium, I d square theta upon dt square is equal to minus mb sin theta. Negative sign with mb sin theta implies that restoring torque is in opposition to deflecting torque. For small values of theta in radians, we approximate sin theta approximately equal to theta and get I d square theta upon dt square is approximately equal to minus mb theta, or d square theta upon dt square is equal to minus mb upon I into theta. This represents a simple harmonic motion. The square of the angular frequency is omega square is equal to mb upon I, and the time period is t is equal to 2 pi square root of I upon mb. Equation number 4, or b is equal to 4 pi square I upon mt square. Equation number 5. An expression for magnetic potential energy can also be obtained on lines similar to electrostatic potential energy. The magnetic potential energy Um is given by is equal to integration of tau theta d theta is equal to integration of mb sin theta d theta is equal to minus mb cos theta. Is equal to minus mb. Equation number 6. The zero of potential energy can be fixed at one's convenience. Taking the constant of integration to be 0 means fixing the zero of potential energy at theta is equal to 90 degree. That is, when the needle is perpendicular to the field. Equation 6 shows that potential energy is minimum is equal to minus mb at theta is equal to 0 degree. That is most stable position, and maximum is equal to plus mb at theta is equal to 180 degree. That is most unstable position. Example 1. In figure, the magnetic needle has magnetic moment 6.7 into 10 raised to minus 2 ampere into meter square and moment of inertia I is equal to 7.5 into 10 raised to minus 6 kilogram into meter square. It performs 10 complete oscillations in 6.70 seconds. What is the magnitude of the magnetic field? Solution. The time period of oscillation is t is equal to 6.70 divided by 10 is equal to 0.67 second. From equation 5, P is equal to 4 pi square I divided by mt square is equal to 4 into 3.14 square into 7.5 into 10 raised to minus 6 divided by 6.7 into 10 raised to minus 2 into 0.67 square is equal to 0.01 Tesla. Example 2. A short bar magnet placed with its axis 30 degree with an external field of 800 Gauss experiences a torque of 0.016 Newton into meter. A. What is the magnetic moment of the magnet? B. What is the work done in moving it from its most stable to most unstable position? C. The bar magnet is replaced by a solenoid of cross-sectional area 2 into 10 raised to minus 4 meter square and 1000 tons but of the same magnetic moment. Determine the current flowing through the solenoid. Solution. A. From equation 3, tau is equal to mb sin theta is equal to 30 degree. Hence, sin 30 degree is equal to 1/2. Thus, 0.016 is equal to m into 800 into 10 raised to minus 4 t into 1/2. M is equal to 160 into 2 divided by 800 is equal to 0.40 ampere into meter square. B. From equation 6, the most stable position is theta is equal to 0 degree and the most unstable position is theta is equal to 180 degree. Work done is given by W is equal to um. Theta is equal to 180 degree minus theta is equal to 0 degree is equal to 2 mb is equal to 2 into 0.40 into 800 into 10 raised to minus 4 is equal to 0.064 joule. C. From equation 30, ms is equal to nia. From part A, ms is equal to 0.40 ampere into meter square. 0.40 is equal to 1000 into I into 2 into 10 raised to minus 4. I is equal to 0.40 into 10 raised to 4 divided by 1000 into 2 is equal to 2a. Example 3. A. What happens if a bar magnet is cut into two pieces? 1. Transverse to its length. 2. Along its length. B. A magnetized needle in a uniform magnetic field experiences a torque, but no net force. An iron nail near a bar magnet, however, experiences a force of attraction in addition to a torque. Why? C. Must every magnetic configuration have a north pole and a south pole? What about the field due to a toroid? D. Two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. We do not know which one. How would one ascertain whether or not both are magnetized? If only one is magnetized, how does one ascertain which one? Solution. A. In either case, one gets two magnets, each with a north and a south pole. B. No force if the field is uniform. The iron nail experiences a non-uniform field due to the bar magnet. There is induced magnetic moment in the nail. Therefore, it experiences both force and torque. The net force is attractive because the induced south pole, say, in the nail is closer to the north pole of magnet than induced north pole. C. Not necessarily. True only if the source of the field has the net non-zero magnetic moment. This is not so for a toroid or even for a straight infinite conductor. D. Try to bring different ends of the bars closer. A repulsive force in some situation establishes that both are magnetized. If it is always attractive, then one of them is not magnetized. In a bar magnet, the intensity of the magnetic field is the strongest at the two ends, means poles, and weakest at the central region. This fact may be used to determine whether A and B is the magnet. In this case, to see which one of the two bars is a magnet, pick up one, say A, and lower one of its ends, first on one of the ends of the other, say B, and then on the middle of B. If you notice that in the middle of B, A experiences no force, then B is magnetized. If you do not notice any change from the end to the middle of B, then A is magnetized. The electrostatic analog. Comparison of equations 2, 3 and 4 with the corresponding equations for electric dipole suggests that magnetic field at large distances due to a bar magnet of magnetic moment m can be obtained from the equation for electric field due to an electric dipole of dipole moment p by making the following replacements. E tends to B, P tends to M, 1 upon 4 pi epsilon 0 tends to mu 0 upon 4 pi. In particular, we can write down the equatorial field, that is BE, of a bar magnet at a distance r, for r is much greater than L, where L is the size of the magnet. BE is equal to minus mu 0 m upon 4 pi r cube. Equation number 7. Likewise, the axial field, that is BA, of a bar magnet for r is much greater than L is BA is equal to mu 0 upon 4 pi into 2m upon r cube. Equation number 8. Equation 8 is just equation 2 in the vector form. Table summarizes the analogy between electric and magnetic dipoles. The dipole analogy. Electrostatics 1 upon epsilon 0. Magnetism mu 0. Dipole moment P M. Equatorial field for a short dipole minus P upon 4 pi epsilon 0 r cube minus mu 0 m upon 4 pi r cube. Axial field for a short dipole 2p upon 4 pi epsilon 0 r cube minus mu 0 2m upon 4 pi r cube. External field torque P into E m into B. External field energy minus PE minus MB. Example 4. What is the magnitude of the equatorial and axial fields due to a bar magnet of length 5.0 cm at a distance of 50 cm from its midpoint? The magnetic moment of the bar magnet is 0.40 ampere meter square. Solution. From equation 7, equatorial field, that is BE. BE is equal to mu 0 m divided by 4 pi r cube is equal to 10 raised to minus 7 into 0.4 divided by 0.5 cube is equal to 10 raised to minus 7 into 0.4 divided by 0.125 is equal to 3.2 into 10 raised to minus 7 Tesla. From equation 8, the axial field, that is BA. BA is equal to mu 0 2m divided by 4 pi r cube is equal to 10 raised to minus 7 into 2 into 0.4 divided by 0.5 cube is equal to 6.4 into 10 raised to minus 7 Tesla. Example 5. Figure shows a small magnetized needle P placed at a point O. The arrow shows the direction of its magnetic moment. The other arrows show different positions and orientation of the magnetic moment of another identical magnetized needle Q. A. In which configuration the system is not in equilibrium? B. In which configuration is the system in 1. Stable and 2. Unstable equilibrium? C. Which configuration corresponds to the lowest potential energy among all the configurations shown? Solution. Potential energy of the configuration arises due to the potential energy of one dipole, say Q, in the magnetic field due to other, that is P. Use the result that the field due to P is given by the expression BP is equal to minus mu 0 upon 4 pi into MP upon R cube, that is on the normal bisector. BP is equal to mu 0 2 upon 4 pi into MP upon R cube, that is on the axis. where MP is the magnetic moment of the dipole P. Equilibrium is stable when MQ is parallel to BP and unstable when it is antiparallel to BP. For instance, for the configuration Q3, for which Q is along the perpendicular bisector of the dipole P, the magnetic moment of Q is parallel to the magnetic field at the position 3. Hence, Q3 is stable. Thus, A. PQ1 and PQ2. B. 1. PQ3, PQ6 stable. 2. PQ5, PQ4 unstable. C. PQ6. Magnetism and Gauss's law. In figure, we see that for a closed surface represented by 1, the number of lines leaving the surface is equal to the number of lines entering it. This is consistent with the fact that no net charge is enclosed by the surface. However, in the same figure, for the closed surface 2, there is a net outward flux, since it does include a net that is positive charge. The situation is radically different for magnetic fields, which are continuous and form closed loops. Examine the Gaussian surfaces represented by 1 or 2 in figure. Both cases visually demonstrate that the number of magnetic field lines leaving the surface is balanced by the number of lines entering it. The net magnetic flux is 0 for both the surfaces. This is true for any closed surface. Consider a small vector area element delta S of a closed surface S as in figure. The magnetic flux through delta S is defined as delta phi B is equal to B delta S, where B is the field at delta S. We divide S into many small area elements and calculate the individual flux through each. Then the net flux phi B is equal to summation of all delta phi B is equal to summation of all B delta S is equal to 0. Equation number 9, where all stands for all area elements delta S dash. Compare this with the Gauss's law of electrostatics. The flux through a closed surface in that case is given by summation of E delta S is equal to Q upon epsilon 0, where Q is the electric charge enclosed by the surface. The difference between the Gauss's law of magnetism and that for electrostatics is a reflection of the fact that isolated magnetic poles, that is also called monopoles, are not known to exist. There are no sources or sinks of B. The simplest magnetic element is a dipole or a current loop. All magnetic phenomena can be explained in terms of an arrangement of dipoles and or current loops. Thus, Gauss's law for magnetism is the net magnetic flux through any closed surface is 0. Example 6. Many of the diagrams given in figure show magnetic field lines, that is thick lines, in the figure wrongly. Point out what is wrong with them. Some of them may describe electrostatic field lines correctly. Point out which ones. Solution. A. Wrong. Magnetic field lines can never emanate from a point. Over any closed surface, the net flux of B must always be 0. That is, pictorially, as many field lines should seem to enter the surface as the number of lines leaving it. The field lines shown, in fact, represent electric field of a long positively charged wire. The correct magnetic field lines are circling the straight conductor. B. Wrong. Magnetic field lines, like electric field lines, can never cross each other because otherwise the direction of field at the point of intersection is ambiguous. There is further error in the figure. Magnetostatic field lines can never form closed loops around empty space. A closed loop of static magnetic field line must enclose a region across which a current is passing. By contrast, electrostatic field lines can never form closed loops, neither in empty space nor when the loop encloses charges. C. Right. Magnetic lines are completely confined within a toroid. Nothing wrong here in field lines forming closed loops, since each loop encloses a region across which a current passes. Note, for clarity of figure, only a few field lines within the toroid have been shown. Actually, the entire region enclosed by the windings contains magnetic field. D. Wrong. Field lines due to a solenoid at its ends and outside cannot be so completely straight and confined. Such a thing violates Ampere's law. The lines should curve out at both ends and meet eventually to form closed loops. E. Right. These are field lines outside and inside a bar magnet. Note carefully the direction of field lines inside. Not all field lines emanate out of a north pole or converge into a south pole. Around both the N pole and the S pole, the net flux of the field is zero. F. Wrong. These field lines cannot possibly represent a magnetic field. Look at the upper region. All the field lines seem to emanate out of the shaded plate. The net flux through a surface surrounding the shaded plate is not zero. This is impossible for a magnetic field. The given field lines, in fact, show the electrostatic field lines around a positively charged upper plate and a negatively charged lower plate. G. Wrong. Magnetic field lines between two pole pieces cannot be precisely straight at the ends. Some fringing of lines is inevitable, otherwise Ampere's law is violated. This is also true for electric field lines. Example 7. A. Magnetic field lines show the direction at every point along which a small magnetized needle aligns at the point. Do the magnetic field lines also represent the lines of force on a moving charged particles at every point? B. Magnetic field lines can be entirely confined within the core of a toroid, but not within a straight solenoid. Why? C. If magnetic monopoles existed, how would the Gauss's law of magnetism be modified? D. Does a bar magnet exert a torque on itself due to its own field? Does one element of a current-carrying wire exert a force on another element of the same wire? E. Magnetic field arises due to charges in motion. Can a system have magnetic moments even though its net charge is zero? Solution. A. No, the magnetic force is always normal to B. Remember, magnetic force is equal to QV into B. It is misleading to call magnetic field lines as lines of force. B. If field lines were entirely confined between two ends of a straight solenoid, the flux through the cross-section at each end would be non-zero. But the flux of field B through any closed surface must always be zero. For a toroid, this difficulty is absent because it has no ends. C. Gauss's law of magnetism states that the flux of B through any closed surface is always zero. Integration S BdS is equal to 0. If monopoles existed, the right-hand side would be equal to the monopole, that is, magnetic charge Qm enclosed by S. Analogous to Gauss's law of electrostatics, integration S BdS is equal to mu0 Qm, where Qm is the monopole magnetic charge enclosed by S. D. No, there is no force or torque on an element due to the field produced by that element itself, but there is a force or torque on an element of the same wire. For the special case of a straight wire, this force is zero. E. Yes, the average of the charge in the system may be zero, yet the mean of the magnetic moments due to various current loops may not be zero. We will come across such examples in connection with paramagnetic material, where atoms have net dipole moment through their net charge is zero. The Earth's magnetism. The strength of the Earth's magnetic field varies from place to place on the Earth's surface, its value being of the order of 10 raised to minus 5 Tesla. What causes the Earth to have a magnetic field is not clear. Originally, the magnetic field was thought of as arising from a giant bar magnet placed approximately along the axis of rotation of the Earth and deep in the interior. However, this simplistic picture is certainly not correct. The magnetic field is now thought to arise due to electrical currents produced by convective motion of metallic fluids that is consisting mostly of molten iron and nickel in the outer core of the Earth. This is known as the dynamo effect. The magnetic field lines of the Earth resemble that of a hypothetical magnetic dipole located at the center of the Earth. The axis of the dipole does not coincide with the axis of rotation of the Earth, but is presently tidal by approximately 11.3 degree with respect to the latter. In this way of looking at it, the magnetic poles are located where the magnetic field lines due to the dipole enter or leave the Earth. The location of the north magnetic pole is at a latitude of 79.74 degree north and a longitude of 71.8 degree west, a place somewhere in North Canada. The magnetic south pole is at 79.74 degree south, 108.22 degree east in the Antarctica. The pole near the geographic north pole of the Earth is called the North Magnetic Pole. Likewise, the pole near the geographic south pole is called the South Magnetic Pole. There is some confusion in the nomenclature of the poles. If one looks at the magnetic field lines of the Earth, one sees that, unlike in the case of a bar magnet, the field lines go into the Earth at the North Magnetic Pole, that is NM, and come out from the South Magnetic Pole, that is SM. The convention arose because the magnetic north was the direction to which the north pole of a magnetic needle pointed. The north pole of a magnet was so named as it was the north-seeking pole. Thus, in reality, the north magnetic pole behaves like the south pole of a bar magnet inside the Earth and vice versa. Example 8. The Earth's magnetic field at the equator is approximately 0.4 Gauss. Estimate the Earth's dipole moment. Solution. From equation 7, the equatorial magnetic field is BE is equal to mu0 m upon 4 pi r cube. We are given that BE is approximately equal to 0.4 Gauss is equal to 4 into 10 raised to minus 5 Tesla. For r, we take the radius of the Earth 6.4 into 10 raised to 6 meter. Hence, m is equal to 4 into 10 raised to minus 5 into 6.4 into 10 raised to 6 whole cube divided by mu0 upon 4 pi is equal to 4 into 10 raised to 2 into 6.4 into 10 raised to 6 whole cube, where mu0 upon 4 pi is equal to 10 raised to minus 7 is equal to 1.05 into 10 raised to 23 ampere into meter square. This is close to the value 8 into 10 raised to 22 ampere into meter square quoted in geomagnetic text. Magnetic declination and dip. Consider a point on the Earth's surface. At such a point, the direction of the longitude circle determines the geographic north-south direction, the line of longitude towards the North Pole being the direction of true north. The vertical plane containing the longitude circle and the axis of rotation of the Earth is called the geographic meridian. In a similar way, one can define magnetic meridian of a place as the vertical plane, which passes through the imaginary line joining the magnetic north and the south poles. This plane would intersect the surface of the Earth in a longitude-like circle. A magnetic needle which is free to swing horizontally would then lie in the magnetic meridian, and the north pole of the needle would point towards the magnetic north pole. Since the line joining the magnetic poles is titled with respect to the geographic axis of the Earth, the magnetic meridian at a point makes angle with the geographic meridian. This, then, is the angle between the true geographic north and the north shown by a compass needle. This angle is called the magnetic declination or simply declination. The declination is greater at higher latitudes and smaller near the equator. The declination in India is small, it being 0 degree 41 minute east at Delhi and 0 degree 58 minute west at Mumbai. Thus, at both these places, a magnetic needle shows the true north quite accurately. There is one more quantity of interest. If a magnetic needle is perfectly balanced about a horizontal axis so that it can swing in a plane of the magnetic meridian, the needle would make an angle with the horizontal. This is known as the angle of dip, that is also known as inclination. Thus, dip is the angle that the total magnetic field BE of the Earth makes with the surface of the Earth. Figure shows the magnetic meridian plane at a point P on the surface of the Earth. The plane is a section through the Earth. The total magnetic field at P can be resolved into a horizontal component HE and a vertical component ZE. The angle that BE makes with HE is the angle of dip I. In most of the northern hemisphere, the north pole of the dip needle tilts downwards. Likewise, in most of the southern hemisphere, the south pole of the dip needle tilts downwards. To describe the magnetic field of the Earth at a point on its surface, we need to specify three quantities, namely the declination d, the angle of dip or the inclination I, and the horizontal component of the Earth's field He. These are known as the element of the Earth's magnetic field. Representing the vertical component by Ze, we have Ze is equal to Be sin I, equation number 10a. He is equal to Be cos I, equation number 10b, which gives 10I is equal to Ze upon He, equation number 10c. What happens to my compass needles at the poles? A compass needle consists of a magnetic needle which floats on a pivotal point. When the compass is held level, it points along the direction of the horizontal component of the Earth's magnetic field at the location. Thus, the compass needle would stay along the magnetic meridian of the place. In some places on the Earth, there are deposits of magnetic minerals which cause the compass needle to deviate from the magnetic meridian. Knowing the magnetic declination at a place allows us to correct the compass to determine the direction of true north. So what happens if we take our compass to the magnetic pole? At the poles, the magnetic field lines are converging or diverging vertically, so that the horizontal component is negligible. If the needle is only capable of moving in a horizontal plane, it can point along any direction, rendering it useless as a direction finder. What one needs in such a case is a dip needle, which is a compass pivoted to move in a vertical plane containing the magnetic field of the Earth. The needle of the compass then shows the angle which the magnetic field makes with the vertical. At the magnetic poles, such a needle will point straight down. Example 9. In the magnetic meridian of a certain place, the horizontal component of the Earth's magnetic field is 0.26 Gauss and the dip angle is 60 degrees. What is the magnetic field of the Earth at this location? Solution. It is given that He is equal to 0.26 Gauss. From figure, we have cos 60 degree is equal to He upon Be. Be is equal to He upon cos 60 degree is equal to 0.26 upon 1/2 is equal to 0.52 Gauss. Earth's magnetic field. It must not be assumed that there is a giant bar magnet deep inside the Earth, which is causing the Earth's magnetic field. Although there are large deposits of iron inside the Earth, it is highly unlikely that a large solid block of iron stretches from the magnetic North Pole to the magnetic South Pole. The Earth's core is very hot and molten, and the ions of iron and nickel are responsible for Earth's magnetism. This hypothesis seems very probable. Moon, which has no molten core, has no magnetic field. Venus has a slower rate of rotation and a weaker magnetic field, while Jupiter, which has the fastest rotation rate among planets, has a fairly strong magnetic field. However, the precise mode of the circulating currents and the energy needed to sustain them are not very well understood. These are several open questions which form an important area of continuing research. The variation of the Earth's magnetic field with position is also an interesting area of study. Charged particles emitted by the sun flow towards the Earth and beyond in a stream called the solar wind. Their motion is affected by the Earth's magnetic field, and in turn, they affect the pattern of the Earth's magnetic field. The pattern of magnetic field near the poles is quite different from that in other regions of the Earth. The variation of Earth's magnetic field with time is no less fascinating. There are short-term variations taking place over centuries and long-term variations taking place over a period of 1,000,000 years. In a span of 240 years, from 1580 to 1820 Anno Domini, over which records are available, the magnetic declination at London has been found to change by 3.5 degrees, suggesting that the magnetic poles inside the Earth change position with time. On the scale of 1,000,000 years, the Earth's magnetic field has been found to reverse its direction. Basalt contains iron, and basalt is emitted during volcanic activity. The little iron magnets inside it align themselves parallel to the magnetic field at that place as the basalt cools and solidifies. Geological studies of basalt containing such pieces of magnetized region have provided evidence for the change of direction of Earth's magnetic field several times in the past. Magnetization and magnetic intensity. The Earth abounds with a bewildering variety of elements and compounds. In addition, we have been synthesizing new alloys, compounds, and even elements. One would like to classify the magnetic properties of these substances. In the present section, we define and explain certain terms which will help us to carry out this exercise. We have seen that a circulating electron in an atom has a magnetic moment. In a bulk material, these moments add up vectorially and they can give a net magnetic moment, which is non-zero. We define magnetization M of a sample to be equal to its net magnetic moment per unit volume. M is equal to mnet upon V. Equation number 11. M is the vector with dimensions L raised to minus 1 A and is measured in a units of ampere per meter. Consider a long solenoid of n turns per unit length and carrying a current I. The magnetic field in the interior of the solenoid was shown to be given by B0 is equal to mu0 into Ni. Equation number 12. If the interior of the solenoid is filled with a material with non-zero magnetization, the field inside the solenoid will be greater than B0. The net B field in the interior of the solenoid may be expressed as B is equal to B0 plus Bm. Equation number 13. Where Bm is the field contributed by the material core. This additional field Bm is proportional to the magnetization M of the material and is expressed as Bm is equal to mu0 M. Equation number 14. Where mu0 is the same constant, permeability of vacuum, that appears in Biot-Savart law. It is convenient to introduce another vector field H called the magnetic intensity, which is defined by H is equal to B upon mu0 minus M. Equation number 15. Where H has the same dimensions as M and is measured in units of ampere per meter. Thus, the total magnetic field B is written as B is equal to mu0 H plus M. Equation number 16. We repeat our defining procedure. We have partitioned the contribution to the total magnetic field inside the sample into two parts. One due to external factors such as the current in the solenoid. This is represented by H. The other is due to the specific nature of the magnetic material, namely M. The latter quantity can be influenced by external factors. This influence is mathematically expressed as M is equal to chi into H. Equation number 17. Where chi, a dimensionless quantity, is appropriately called the magnetic susceptibility. It is a measure of how a magnetic material responds to an external field. It is small and positive for materials, which are called paramagnetic. It is small and negative for materials, which are termed diamagnetic. In the latter case, M and H are opposite in direction. From equations 16 and 17, we obtain B is equal to mu0 1 plus chi H. Equation number 18 is equal to mu0 mu r h is equal to mu h. Equation number 19, where mu r is equal to 1 plus chi is a dimensionless quantity called the relative magnetic permeability of the substance. It is the analog of the dielectric constant in electrostatics. The magnetic permeability of the substance is mu, and it has the same dimensions and units as mu 0. Mu is equal to mu 0 mu r is equal to mu 0 1 plus chi. The three quantities chi, mu r and mu are interrelated and only one of them is independent. Given one, the other two may be easily determined. Magnetic susceptibility of some elements at 300 Kelvin. Diamagnetic substance chi, paramagnetic substance chi. Bismuth minus 1.66 into 10 raised to minus 5. Aluminium 2.3 into 10 raised to minus 5. Copper minus 9.8 into 10 raised to minus 6. Calcium 1.9 into 10 raised to minus 5. Diamond minus 2.2 into 10 raised to minus 5. Chromium 2.7 into 10 raised to minus 4. Gold minus 3.6 into 10 raised to minus 5. Lithium 2.1 into 10 raised to minus 5. Lead minus 1.7 into 10 raised to minus 5. Magnesium 1.2 into 10 raised to minus 5. Mercury minus 2.9 into 10 raised to minus 5. Niobium 2.6 into 10 raised to minus 5. Nitrogen, that is standard temperature and pressure, minus 5.0 into 10 raised to minus 9. Oxygen, that is standard temperature and pressure, 2.1 into 10 raised to minus 6. Silver, minus 2.6 into 10 raised to minus 5. Platinum, 2.9 into 10 raised to minus 4. Silicon, minus 4.2 into 10 raised to minus 6. Tungsten, 6.8 into 10 raised to minus 5. Example 10. A solenoid has a core of a material with relative permeability 400. The windings of the solenoid are insulated from the core and carry a current of 2 ampere. If the number of turns is 1000 per meter, calculate A, H, B, M, C, B and D. The magnetizing current IM. Solution. A. The field H is dependent on the material of the core and is H is equal to Ni is equal to 1000 into 2.0 is equal to 2 into 10 raised to 3 ampere per meter. B. The magnetic field B is given by B is equal to mu r mu 0 H is equal to 400 into 4 pi into 10 raised to minus 7 Newton per ampere square into 2 into 10 raised to 3 ampere per meter is equal to 1.0 Tesla. C. Magnetization is given by M is equal to B minus mu 0 H upon mu 0 is equal to mu r mu 0 H minus mu 0 H upon mu 0 is equal to mu r minus 1 H is equal to 399 into H is approximately equal to 8 into 10 raised to 5 ampere per meter. D. The magnetizing current IM is the additional current needs to be passed through the winding of the solenoid in the absence of the core, which would give a B value as in the presence of the core. Thus, B is equal to mu 0 N I plus IM. Using I is equal to 2 ampere. B is equal to 1 Tesla. IM is equal to 794 ampere. Magnetic properties of materials. The discussion in the previous section helps us to classify materials as diamagnetic, paramagnetic or ferromagnetic. In terms of the susceptibility, chi, a material is diamagnetic if chi is negative, para if chi is positive and small, and ferro if chi is large and positive. A glance at table gives one a better feeling for these materials. Here, epsilon is a small positive number introduced to quantify paramagnetic materials: diamagnetic, paramagnetic, ferromagnetic. -1 is less than or equal to chi less than 0. 0 is less than chi less than epsilon. Chi is very much greater than 1. 0 is less than or equal to mu r less than 1. 1 is less than mu r less than 1 plus epsilon. Mu r is very much greater than 1. Mu is less than mu 0. Mu is greater than mu 0. Mu is very much greater than mu 0. Dimagnetism. Diamagnetic substances are those which have tendency to move from stronger to the weaker part of the external magnetic field. In other words, unlike the way a magnet attracts metals like iron, it would repel a diamagnetic substance. Figure shows a bar of diamagnetic material placed in an external magnetic field. The field lines are repelled or expelled, and the field inside the material is reduced. In most cases, this reduction is slight, being 1 part in 10⁵. When placed in a non-uniform magnetic field, the bar will tend to move from high to low field. The simplest explanation for dimagnetism is as follows. Electrons in an atom orbiting around nucleus possess orbital angular momentum. These orbiting electrons are equivalent to current-carrying loop and thus possess orbital magnetic moment. Diamagnetic substances are the ones in which resultant magnetic moment in an atom is 0. When magnetic field is applied, those electrons having orbital magnetic moment in the same direction slow down, and those in the opposite direction speed up. This happens due to induced current in accordance with Lenz's law. Thus, the substance develops a net magnetic moment in direction opposite to that of the applied field and hence repulsion. Some diamagnetic materials are bismuth, copper, lead, silicon, nitrogen at standard temperature and pressure, water and sodium chloride. Dimagnetism is present in all the substances. However, the effect is so weak in most cases that it gets shifted by other effects like paramagnetism, ferromagnetism, etc. The most exotic diamagnetic materials are superconductors. These are metals cooled to very low temperatures which exhibits both perfect conductivity and perfect diamagnetism. Here, the field lines are completely expelled. Chi is equal to -1 and mu r is equal to 0. A superconductor repels a magnet and, that is by Newton's third law, is repelled by the magnet. The phenomenon of perfect diamagnetism in superconductors is called the Meissner effect, after the name of its discoverer. Superconducting magnets can be gainfully exploited in variety of situations. For example, for running magnetically levitate superfast trains. Paramagnetism. Paramagnetic substances are those which get weakly magnetized. When placed in an external magnetic field, they have tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get weakly attracted to a magnet. The individual atoms or ions or molecules of a paramagnetic material possess a permanent magnetic dipole moment of their own. On account of the ceaseless random thermal motion of the atoms, no net magnetization is seen. In the presence of an external field B0, which is strong enough, and at low temperatures, the individual atomic dipole moment can be made to align and point in the same direction as B0. Figure shows a bar of paramagnetic material placed in an external field. The field lines gets concentrated inside a material and the field inside is enhanced. In most cases, this enhancement is slight, being 1 part in 10⁵. When placed in a non-uniform magnetic field, the bar will tend to move from weak field to strong. Some paramagnetic materials are aluminum, sodium, calcium, oxygen, that is at standard temperature and pressure, and copper chloride. Experimentally, one finds that the magnetization of a paramagnetic material is inversely proportional to the absolute temperature T. M is equal to C B0 upon T, equation number 20a. Or equivalently, using equations, B0 is equal to mu0 Ni and M is equal to chi h. Chi is equal to C mu0 upon T, equation number 20b. This is known as Curie's law. After its discoverer, Pierre Curie, 1859 to 1906, the constant C is called Curie's constant. Thus, for a paramagnetic material, both chi and mu r depend not only on the material but also in a sample fashion on the sample temperature. As the field is increased or the temperature is lowered, the magnetization increases until it reaches the saturation value Ms, at which point all the dipoles are perfectly aligned with the field. Beyond this, Curie's law is no longer valid. Ferromagnetism. Ferromagnetic substances are those which get strongly magnetized when placed in an external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field. That is, they get strongly attracted to a magnet. The individual atoms or ions or molecules in a ferromagnetic material possess a dipole moment as in a paramagnetic material. However, they interact with one another in such a way that they spontaneously align themselves in a common direction over a microscopic volume called domain. The explanation of this cooperative effect requires quantum mechanics and is beyond the scope of this textbook. Each domain has a net magnetization. Typical domain size is 1 mm and the domain contains about 10⁻11 atoms. In the first instant, the magnetization varies randomly from domain to domain and there is no bulk magnetization. This is shown in figure. When we apply an external magnetic field B0, the domains orient themselves in the direction of B0 and simultaneously the domain oriented in the direction of B0 grow in size. This existence of domains and their motion in B0 are not speculations. One may observe this under a microscope after sprinkling a liquid suspension of powdered ferromagnetic substance of samples. This motion of suspension can be observed. Figure shows the situation when the domains have aligned and amalgamated to form a single giant domain. Thus, in a ferromagnetic material, the field lines are highly concentrated. In non-uniform magnetic field, the sample tends to move towards the region of high field. We may wonder as to what happens when the external field is removed. In some ferromagnetic materials, the magnetization persists. Such materials are called hard magnetic materials or hard ferromagnets. Alnico, an alloy of iron, aluminium, nickel, cobalt and copper is one such material. The naturally occurring lodestone is another. Such materials form permanent magnets to be used among other things as a compass needle. On the other hand, there is a class of ferromagnetic materials in which the magnetization disappears on removal of the external field. Soft iron is one such material. Appropriately enough, such materials are called soft ferromagnetic materials. There are a number of elements which are ferromagnetic: iron, cobalt, nickel, gadolinium, etc. The relative magnetic permeability is greater than 1000. The ferromagnetic property depends on temperature. At high enough temperature, a ferromagnet becomes a paramagnet. The domain structure disintegrates with temperature. This disappearance of magnetization with temperature is gradual. It is a phase transition reminding us of the melting point of a solid crystal. The temperature of transition from ferromagnetic to paramagnetism is called the Curie temperature Tc. Table lists the Curie temperature of certain ferromagnets. The susceptibility above the Curie temperature, that is, in paramagnetic phase, is described by chi is equal to C upon T minus Tc, where T is greater than Tc. Equation number 21. Curie temperature Tc of some ferromagnetic materials. Material Tc, that is Kelvin. Cobalt 1394. Iron 1043. Fe2O3 893. Nickel 631. Gadolinium 317. Example 11. A domain in ferromagnetic iron is in the form of a cube of side length 1 micrometer. Estimate the number of iron atoms in the domain and the maximum possible dipole moment and magnetization of the domain. The molecular mass of iron is 55 gram per mole and its density is 7.9 gram per centimeter cube. Assume that each iron atom has a dipole moment of 9.27 into 10 raised to minus 24 ampere meter square. Solution. The volume of the cubic domain is V is equal to 10 raised to minus 6 meter whole cube is equal to 10 raised to minus 18 meter cube is equal to 10 raised to minus 12 centimeter cube. Its mass is volume into density is equal to 7.9 gram per centimeter cube into 10 raised to minus 12 centimeter cube is equal to 7.9 into 10 raised to minus 12 gram. It is given that Avogadro number, that is 6.02 into 10 raised to 23 of iron atoms have a mass of 55 gram. Hence, the number of atoms in the domain is N is equal to 7.9 into 10 raised to minus 12 into 6.023 into 10 raised to 23 upon 55 is equal to 8.65 into 10 raised to 10 atoms. The maximum possible dipole moment Mmax is achieved for the unrealistic case when all the atomic moments are perfectly aligned. Thus, M maximum is equal to 8.65 into 10 raised to 10 into 9.27 into 10 raised to minus 24 is equal to 8.0 into 10 raised to minus 13 ampere meter square. The consequent magnetization is M maximum is equal to M maximum upon domain volume is equal to 8.0 into 10 raised to minus 13 ampere meter square upon 10 raised to minus 18 meter cube is equal to 8.0 into 10 raised to 5 ampere per meter. The relation between B and H in ferromagnetic materials is complex. It is often not linear and it depends on the magnetic history of the sample. Figure depicts the behavior of the material as we take it through one cycle of magnetization. Let the material be unmagnetized initially. We place it in a solenoid and increase the current through the solenoid. The magnetic field B in the material rises and saturates as depicted in the curve OA. This behavior represents the alignment and merger of domains until no further enhancement is possible. It is pointless to increase the current and hence the magnetic intensity H beyond this. Next, we decrease H and reduce it to 0. At H is equal to 0, B is not equal to 0. This is represented by the curve AB. The value of B at H is equal to 0 is called retentivity or remnants. In figure, Br is approximately equal to 1.2 Tesla, where the subscript R denotes retentivity. The domains are not completely randomized, even though the external driving field has been removed. Next, the current in the solenoid is reversed and slowly increased. Certain domains are flipped until the net field inside stands nullified. This is represented by the curve BC. The value of H at C is called coercivity. In figure, Hc is approximately equal to minus 90 ampere per meter. As the reversed current is increased in magnitude, we once again obtain saturation. The curve CD depicts this. The saturated magnetic field Bs is approximately equal to 1.5 Tesla. Next, the current is reduced, that is curve DE, and reversed, that is curve EA. The cycle repeats itself. Note that the curve OA does not retrace itself as H is reduced. For a given value of H, B is not unique but depends on previous history of the sample. This phenomenon is called hysteresis. The word hysteresis means lagging behind and not history. Permanent magnets and electromagnets. Substances which at room temperature retain their ferromagnetic property for a long period of time are called permanent magnets. Permanent magnets can be made in a variety of ways. One can hold an iron rod in the north-south direction and hammer it repeatedly. The method is illustrated in figure. The illustration is from a 400-old book to emphasize that the making of permanent magnets is an old art. One can also hold a steel rod and stroke it with one end of a bar magnet a large number of times, always in the same sense to make a permanent magnet. An efficient way to make a permanent magnet is to place a ferromagnetic rod in a solenoid and pass a current. The magnetic field of the solenoid magnetizes the rod. The hysteresis curve allows us to select suitable materials for permanent magnets. The material should have high retentivity so that the magnet is strong and high coercivity so that the magnetization is not erased by stray magnetic fields, temperature fluctuations, or minor mechanical damage. Further, the material should have high permeability. Steel is one favored choice. It has a slightly smaller retentivity than soft iron, but this is outweighed by the much smaller coercivity of soft iron. Other suitable materials for permanent magnets are steel, alnico, cobalt steel, and ticonal. Core of electromagnets are made of ferromagnetic materials, which have high permeability and low retentivity. Soft iron is a suitable material for electromagnets. On placing a soft iron rod in a solenoid and passing a current, we increase the magnetism of the solenoid by 1,000-fold. When we switch off the solenoid current, the magnetism is effectively switched off since the soft iron core has a low retentivity. The arrangement is shown in figure. In certain applications, the material goes through an AC cycle of magnetization for a long period. This is the case in transformer cores and telephone diaphragms. The hysteresis curve of such materials must be narrow. The energy dissipated and the heating will consequently be small. The material must have a high resistivity to lower eddy current losses. Electromagnets are used in electric bells, loudspeakers, and telephone diaphragms. Giant electromagnets are used in cranes to lift machinery and bulk quantities of iron and steel.